So now consider two events. If the intersection is the empty set, they're mutually exclusive. So given the probabilities of the individual events, we can easily find the probability of the intersection, well, it's the empty set, and the probability of their union. But what if they're not mutually exclusive? We can represent the situation using a Venn diagram. The most general Venn diagram for two events is shown, and note there are three regions. The part in A only, which we can write as the set difference A minus B. Remember, given two sets A and B, the set difference is the set of elements in the first that are not in the second. There's the part in B only, which we can write as the set difference B minus A, and the overlap, which we can write as just the intersection of the two sets. And for notational convenience, we'll let that intersection be the third set C. Then A can be written as A minus B union C, and note that these two events are mutually exclusive. Well, don't believe me just because I'm on the internet. Suppose X is in the set difference. Then by definition, we know that X is in A and not in B, so it's certainly not in the intersection. Don't forget to check the converse. Suppose X is in the intersection. Then by definition, X has to be in A and also in B, so it can't be in the set difference. So if an outcome is in one set, it can't be in the other. And so these two sets are mutually exclusive. And since the events are mutually exclusive, we can write the probability of A as the sum of the probabilities. Or, rearranging, we find the probability of the difference. Now, by the same argument, the probability of B is the same as the probability of B minus A plus the probability of C. And finally, the union consists of those three mutually exclusive events, and so the probability could be written as the sum of those three probabilities. But the probability of A minus B is the probability of A minus the probability of C. The probability of B minus A is the probability of B minus the probability of C. And so if we simplify, we get, and we can rearrange and conclude that for all events A and B, the probability of the union plus the probability of the intersection is the sum of the probabilities. Now consider an event and its complement. We have the probability of the union plus the probability of the intersection is the sum of the probabilities of the individual events. But by definition, the union of an event and its complement is the entire sample space, and, again, by definition, the intersection is going to be the empty set. And so we have the probability of S plus the probability of the empty set is the sum of the two probabilities, but the probability of the sample space is 1, and the probability of the empty set is nothing, and so we have, and so we can find. And so for any event A, the probability of its complement is 1 minus the probability of the event itself. So suppose the probability a student takes math is 0.6. What's the probability they didn't take math? So if we let M be the event that a student took math, then the probability of M is 0.6. The event that they didn't take math is the complement, and so we find the probability of the complement is 1 minus the probability of the event, 0.4. So suppose the probability a student takes math is 0.6, the probability they take English is 0.5, and the probability they take both is 0.4. What's the probability a student took at least one? Let M be the event a student takes math, and E the event that they take English. So our formula tells us, and we know the probability they take math, the probability they take English, and take both means they have taken both math and English, so that's the probability of their intersection. Take at least one means that they have either taken math or English, so we want the probability of their union. So we can substitute in the given values and solve for the probability of their union, 0.7. Now, it's often useful to work with the complements. We have the complement of a union is the intersection of the complements, and the complement of an intersection is the union of the complements. So the thing to note here is that we're taking the complements of both and we're changing the intersection to a union. So let M be the event a student took math and E the event a student took English. How do you describe the students who took neither? If a student didn't take math, this corresponds to the event M complement. Likewise, if they didn't take English, so taking neither is the intersection of the complements. Now, a useful strategy when working with probability is to find all equivalent formulations because one of them will probably be easier to work with than the others. So even though taking neither can be described this way, we note that De Morgan's law also allows us to describe it as the complement of the union. So let's consider the same problem as before. We actually want to find the probability of didn't take math and also didn't take English. And we note that this is the complement of the union. So if we can compute the probability of the union, we can find the probability of the complement. Well, we actually determined that already. The probability of the union is 0.7, and so the probability of the complement is 1 minus that number, 0.3.